in here. Cool.
Okay, great. So I just want to say thank you all for coming to this session today. I hope that you'll enjoy it. My name is Alex, and I've been working as a software engineer for quite a few years now. I used to work in big tech companies before, and I've been in finance for the past 4.5 years. And I'm always very excited when I get to work with algorithms or data structures at my job. So I'm also very excited to talk about trees and graphs today here with you. Trees and graphs are special sorts of data structures. And I just want to quickly say that my talk today is tailored for complete beginners. So people who haven't really heard much about trees and graphs before. So we'll focus on the core concepts today. We'll look at the very basic algorithms, and we'll do some practice. My talk will take about 35 to 40 minutes, and then we'll do some practice sessions in breakout rooms. I'll start with trees, and then we'll move on to graphs. Right. Cool. So the first question, obviously, is what is a tree and why are trees important? So we define a tree as a directed, acyclic, and hierarchical structure of linked nodes. And that's quite a heavy definition, isn't it? So let's just talk through it and dive deep into it and understand what it actually means. So there is an illustration of a typical tree here on the right side. Sorry, just a second. First of all, what you can see from this picture is that this structure looks hierarchical because there is one node at the top, then there are a couple of nodes, one layer below, there are some more nodes below that, and so on. So there is some vertical structure in this object. That's why we say that a tree is a hierarchical structure. You can also see that there are links between the nodes, between the elements of the tree, and these links have direction. They go only one way. They go from top to the bottom, but not the other way around. That's why it's directed. And finally, it's acyclic, which means that, let's say we start at one node at the top, and then we follow one of the links towards one of its neighbors. This link has a direction, so we can't really, there is no other link which leads us back to our top node. So there is really no cycle in this structure. There are no cycles, hence the structure is acyclic. So I hope that the definition is a bit clearer now. So I used the term node a couple of times. So a node is really, it's an element in the tree. So here you see that we have this round elements, each of which has an integer value associated with it, like 2 or 10 or 5. For simplicity, we'll just assume that each node just has an integer associated with it, and that's it. However, I just wanted to note that in practice, oftentimes there is an integer key associated with each node, but there is also an object, really an arbitrary object, a data value, which each node has. And the reason for that is because it's quite easy to operate with integers. It's easy to identify each node within the tree, find a place for each node just using these integers. And but we might use the tree to store some information about more complicated objects, and hence why we might, in practice, we often have a data value in each node as well. However, as I said, for the purpose of this talk, we're just going to focus on the nodes which have integer keys in them, and that's it. I already mentioned that each tree has a root, and in this case, it's node 2 at the very top. And just a bit more terminology for the trees. Nodes in the trees have directed links to other nodes, and the nodes which these links are directed to are typically called children. And finally, you can notice that there are a few nodes at the very bottom which have no outgoing links from them. And these nodes are called leaves. So in this particular tree, such nodes are 2, 10, 5, 11, and 4. So that's the basic idea and the definition of a general tree. So why do we care about the structure so much? Why is it important? So the thing is that it's really good for representing objects which have some sort of hierarchy in them. For example, if you think about a company, how a company is structured, there is normally a person at the top, like a chief executive officer. Then there are other senior leadership people who report to the CEO directly. Then there are more people who report to these senior managers, and more people who report to the middle managers, and so on and so forth. And you can easily imagine this structure as a tree. I would like to talk a bit more about more technical examples of the trees, more technical use cases, where we might choose to represent our objects, our data in the trees. And the first thing that I would like to chat about is our language, natural language. Let's look at the sentence which I have right here. I shot an elephant in my pajamas. So sorry for this, by the way. I did not make this picture. There are, if we think about the syntax of this sentence, we would see that there is the main subject in the sentence, which is I, and there is the verbal phrase of the sentence, which is short. Short, well, an elephant in my pajamas. And diving further in the sentence, we can just separate phrases, separate bits of the sentence which belong together, which are structured together, and they all come together to form the sentence at the very top. So we here have the root, which represents the whole of the sentence. Then we have one child, which represents a noun phrase, which is just I. Then we have the second child of the root, which is the verbal phrase, which is basically the rest of the sentence. Then this rest of the sentence can be further split into another verbal phrase and the prepositional phrase, and so on and so forth. So hence we get a number of leaves in the sentence, which are words that form it. Another nice example of when a tree might be useful is representation of mathematical expressions. So here you see that we have an expression which is basically a sum of two parts, and the first part is the product of two parts, and the first part of the product is the sum of two parts again. And this can be nicely represented with a tree where each of the node has two children, well, or no children if it's a leaf. I think I'm going to move on to the next slide, but I realized that I forgot to mention, if you have any questions in the process, feel free to just unmute yourself and ask, or maybe post them in our chat, and maybe our moderators will nicely monitor the chat and ask any questions that you might have in the process of the presentation. Really don't worry about holding your questions back. It's fine. Feel free to ask them anytime. Right, so now I just like to show you how we might implement a tree structure, or rather a tree node. And really, it's a very, very laconic piece of code in Python. And yeah, just wanted to mention that I will be using Python for the whole of my talk today. Don't worry if you're not proficient with it. I hope that it would be quite readable. But again, if you have any questions, feel free to ask. So here, each node will have a some data object, which, as we agreed before, would just be an integer. And also each node will have links to its children. And since it can have an arbitrary number of children, we just store a list here. So we can just append as many children as we want to each node. And here you can see a little example on the right side when we create a root with the key 0. Then we have three other nodes, and we arrange them into the tree so that root has 2 children, C1 and C2, and C1 has 1 child, which is C3. So you see that we can take the root and we can print all its children, and we'll just see the 2 nodes which correspond to C1 and C2. So I hope that's a pretty clear and laconic way to implement a tree in Python. I see that there are some pop-ups in the chat, although I can't open the chat because I'm sharing my screen. So Irina, maybe you could have a look if there are any questions there.
Yeah, I'm looking. I don't see anything that you can answer, I suppose.
Okay, that's all right. Just checking.
Don't worry, it's mostly me spamming.
Okay, that's fine. I can just see that there are new messages in the chat, but I can't actually see the messages. So I was wondering if these are questions. Cool. Okay, moving on. I want to chat about a special kind of tree. And this is called binary tree. And really the rule for the binary tree is very simple. It is a tree where each node can have only up to 2 children, but never more than 2 children. So you can see an example on the right side. You can see that 6, for example, has pointers to 5 and 11, and there are no more nodes that it can point at. So this makes the implementation a little bit easier in a way, because instead of storing a list of an arbitrary number of nodes, we can just store 2 pointers, a pointer to the left child and a pointer to the right child. And we know that that would be it. By the way, going back to my real life examples of trees, you might notice that both of them are actually binary trees. So, okay, now the first algorithm, exciting. I would just like to think a bit about, given a tree, how would we print it? How would we go through all the nodes that we have in the tree if, let's say, we only have the link to the root? And by the way, that's very common. When you have a tree, it's very common to just refer to the root as the tree, because really you can follow the links from the root and you can access any node in the tree from the root. So anyway, let's take the binary tree which I have right here. And let's have a think at how we might, what we can do to print it out. And the way we're going to print it out is for each node, first we're going to print the value or the key of this node. Then we're going to print everything that's to the left of this node. And after this, we're going, oh no, sorry, yeah, I got a bit confused. So that's not it. We're actually printing it in a slightly different way for this task. We would like to print it left to right. So in this particular case, we would start with 2, which is the leftmost node, then it would be 7, then it would be 5 at the very bottom, followed by the 7, and so on and so forth. So this is called in-order traversal, because if you think about it, what we're doing is for each node, first we print everything that's to the left of this node, then we print the key of this node itself, and then we print everything that's to the right side of this node. So it's a very nice and simple recursive program. As you see, that there is a little snippet of code here which does exactly this, traversal. So what we need to do, given the node or given the root, we need to check if this node has any children to the left-hand side, because if it doesn't have any, then there is nothing to print, which is a win. If it does, however, we can take its left child, and we know that there can only be one left child because it's a binary tree, and we can just repeat this procedure for this left node, as we trust that this procedure will print the left node in exactly the same manner as the root. Once we're all done with the left, subtree, we can print the data from the root, and then we repeat the procedure for the right child, for the right subtree. If you think, if you just look at how the leaves are treated by this procedure, you will see that the leaves don't have any children. They don't have either left or the right child. So what it would do, it would just print the data for each of the leaves. And again, if you look at the nodes which are one way upwards from the leaves, you'll realize that it would print the left leaf first, then it will print the parent of this leaf, and then it will print the right child of this leaf. So hopefully, yeah, hopefully that's nice and clear. And now I want to chat about another special kind of the tree, which is a special case of the binary tree, and it's called the binary search tree. And there are a couple of more, so basically we take a binary tree and we just impose a couple more restrictions on this tree. So still, each node has at most 2 children, as in a normal binary tree. We assume that all the keys in the binary search tree are unique. It is not necessarily the case, but we'll assume it for the purpose of this talk. And there are 2 important assumptions in binary search trees, or BSTs, and that is that every node key is greater than the key of its left child, and it is less than the key of its right child. And I have an example of the binary tree right here, and you can see that the root, for example, is 8, and there is a 3 to the left side of the root, which is clearly less than 8. However, 3 has the right child, which has the key 6, and this is greater than 3. But you might note that it is still smaller than 8, than the root, and it makes perfect sense because Well, because we know that whenever this element 6 was added to the tree, it was compared to the root, and had it been greater than the root, it would have gone to the right side. So there is this nice property of the binary search tree that whenever you take a node, everything that's to the left side of this node is always less than this node value. And everything that's to the right side of this node is always greater than this node's value. So that's the definition of the binary search tree. And well, a natural question that arises is, why do we need it at all? Why do we bother with these restrictions? And let's just have a think about, given a tree, what would we do to find an element in this tree? So let's say we have this tree on the right, and let's say someone asks us a question. Can you tell me if 7 is in this tree or if it's not in this tree? So how would you go about that? A nice property of the binary tree, as we just covered, is that everything that's to the left side of the root is smaller than the root, which is 8 in this case, and everything that's to the right side of the root is greater than 8. So we can argue that if 7 is in our tree, then it should definitely be to the left side of 8. So it can only be in the left subtree of the root. So it would be enough if we just take the left subtree and check whether 7 is in there or not. We don't really have to bother with checking the right subtree, which is not true in the general case of a binary tree or even the general case of any tree, because there are no restrictions on the values of the keys, and we would not be able to guarantee that it's only enough to check one of the subtrees at every single step. So yeah, that's why binary search trees are nice, and that's why they're called search trees, because it's easy to search elements in this binary.
There is a small question.
Mm-hmm.
Do keys start at 0?
Well, not necessarily. I mean, in a general case, not necessarily. I mean, it depends. They don't have to start at 0. They don't even have to be integers. It's just for the sake of simplicity in this talk, we're just assuming they're integers which are reasonably small, because we are talking about a small trees.
Yeah.
Cool. Okay. So yeah, just wanted to reiterate on how the search would work. We'll have the access to the root, which is 8 in this case, and let's say we are asked to find an element which is 7. So what we would do, we would compare the element to the root. We will figure out whether the element should be on the left side or on the right side of the root. We will take either the left subtree or the right subtree. In this case, it will be the left subtree, which will start with 3. And then we'll repeat this procedure recursively. So we will compare 7 to 3, and we will realize that 7 is greater than 3. So we need to take the right subtree of 3, which is, in this case, a small subtree starting with 6, and so on and so forth. If we, when comparing the keys of the nodes, if we find the key which we were looking for, then great. Then the answer is obviously yes, this node is in the tree. If we get to the leaf and realize that we haven't come across the value that we were hoping to find, then the answer is that this element is not in our BST, because we know that there can only be one unique path from the root to the leaf, which might either contain the desired element or not. So now let's just think a bit about how long this search procedure would take us. Well, it's always useful to think of the worst case. So what's the worst case would be for such a structure? And clearly the worst case is when you have to check every single element in the binary search tree. And is it really possible, you might ask? It is possible if you think about a tree which represents just one sorted sequence where every node has only one child. So something like 5, 4, 3, 2, 1, starting with 5. Then yes, the worst case is you just have to go through all the elements in this tree, and well, this tree can be really big, and this sequence can be really, really long. So you'll have to visit all the elements of the tree. So if you have n elements, then your query, your search operation will actually be linear in terms of n. So yeah, we just chatted about find, so that's just a little bit of a reminder. We begin at the root. If the element which we want to find is smaller than the current node, we move left. If it's larger, then we move right. If we reach a leaf and still haven't found our element, then it's not in the tree. Now, just want to cover another operation on the BST, which is very useful. And this has to do with how the tree is populated, or rather how the new nodes are added to the tree. And the rule is that whenever you need to add a rule to the tree, you always insert it as leaf. So what you do is you find the right leaf place for this node, following exactly the same procedure as with the search operation. And then once you find the right position for the new node, you just append it to its parent. So in this case, when we insert 8, we first need to find the new node's location, that is the parent, which will have 8 as its child. We'll start at the root. We'll realize that 8 is greater than 4, so we move on to 6. We realize that 8 is greater than 6, so we move on to 7. We see that we reached the leaf of this tree, so we need to add 8 as one of the children for the 7. And since 8 is clearly greater than 7, we add 8 as the right child. So as we just discussed, the worst case in terms of time spent on the search operation is linear. If you think of a tree as a sorted sequence, you'll probably have to visit all the nodes in this sequence. However, let's think a bit about what if the tree is not that naughty. What if it's more or less nicely structured and balanced? And by balanced, let's say that all the subtrees for each of the nodes are always of equal length. So if you think of a sorted sequence as a tree, there is, as we agreed, there is only one child for each node. So the subtree, so one of the subtrees has always length 0, and another subtree can have an arbitrary big length, which is clearly not what we're hoping for here, but rather we would hope that for each node, we will always have the left and the right subtrees, which are of the same size. And here is a little picture in the right bottom corner of what's called the full binary tree. And that's basically a tree where every single node, apart from the leaves, of course, has 2 children. So what would be So given this tree, which has, let's say, n elements, what would be the complexity of the find operation in this case? So let's have a think. What's the worst case in this scenario? At worst, you need to go down all the way to the leaf to find a node. Let's say you don't come across this node midway. You need to go all the way down. So the question is, what is the height of this tree? How many hops do we need to do to reach the leaf? And the beauty here is that it takes exactly the same number of hops to reach every leaf in this tree, because it's a full binary tree. Right, how do we estimate the height of this full binary tree with n nodes? So you can notice that if we look at level 0, which only have one node, and let's say we want to add another layer to our tree, how many nodes will have them compared to the previous layer? Well, in order to do this, we will need to add the right child and the left child, right? So that would be 2 more nodes, and that would be twice as many nodes on level 1 as level 0. Now let's say that we want to add another layer to the binary tree, and this will require adding 4 nodes now, because we need to add both the left child and the right child to each of the leaf nodes, and that would be 4 new nodes, and again, twice as much nodes as on the previous layer, and so on and so forth. So what is the length of this path then? You might notice that in this case, in level 0, we have 1 node, which is 2 to the power of 0. On the level 2, we have 2 nodes, which is 2 to the power of 1, and so on and so forth. So thinking of the height of this tree, it would appear that the height is exactly the logarithm with base 2 of our number of nodes, which is n. So that would mean that it will take us only log n hops to answer the question whether a node is in the tree or not, which is clearly an improvement from the linear complexity. And that's why we care about this tree so much. However, it's important to note that the standard binary search tree is not necessarily full. It's not necessarily balanced. It can be anything. So in practice, other types of trees which are more restrictive are used. And there is like a big class of trees which are called self-balancing trees. And those are the ones that maintain certain assumptions about the heights of the subtrees for each node. For example, in an AVL tree, you can assume that the difference between the left subtree, the length of the left subtree and the length of the right subtree is at most 1. So they are roughly the same length. And imposing this assumption or other similar assumptions in other kinds of trees helps us keep this logarithmic complexity and move away from the linear operation. So finally, I just wanted to give a few pointers to other special kinds of trees. I will not talk about those in detail because we need to move on and talk about graphs, but it's just for the curious ones. So quad tree is a tree where each node has exactly 4 children, and it's used quite a lot in spatial indexing and maps. And our tree, sorry. And our trees are based on minimum bounding rectangles. If you think about the plane and the rectangles which are drawn on this plane, and they can contain each other, and our trees is deduced from these relationships. I would also like to say a couple of words about the B trees. B trees generalize the BSTs, the binary search trees, and they allow nodes to have more than 2 children. And this is a special kind of balanced tree, which is used in storage systems, which are designed to read and write vast quantities and blocks of data, such as disks. Right, so I'm going to move on to the graphs now. Again, feel free to ask any questions in the chat or just ask them directly. So what is a graph? We define a graph as a structure which is made of V nodes or vertices and E connections between these nodes, which we call edges. Unlike the tree, it is not a hierarchical structure. It does not have to be a directed structure, and it doesn't even have to be in a cyclic structure. However, trees are graphs. Trees are actually a special case of graphs. Here you can see an example of a graph which has 6 vertices and 7 edges. This graph is not directed. For example, there is no indication of the direction in the link between 4 and 6. So why do we care about graphs? Graphs are generally good for representing objects which have dependencies between each other. For example, you might think about towns on a map as vertices and roads between them as edges. It is basically a graph. I said that graphs don't have to be directed, they can be directed. However, so undirected graphs are the graphs where edges don't have orientation, and we say that if there is an edge between a pair of vertices, then each vertex is reachable from another. For example, for this little graph, 4 is reachable from 6, and at the same time, 6 is reachable from 4. However, there are directed graphs, and these are graphs with the limitation that their edges actually have the direction, they have orientation. If there is a link, if there is an edge between the 2 vertices, it doesn't mean that one is necessarily reachable from the other one and vice versa. So for example, in the graph that I have here on the right side, you can see that there is a link between the node which is indexed with 0,2 and 2,0. However, you can go from 0,2 to 2,0, but you can't go the other way around. If you want to have a graph where you can go the other way around, you need to have 2 edges between the nodes, like we have here between 1,1 and 2,2. And as I said, graphs don't have to be cyclic, they can have cycles, and you can see a cycle here in this directed graph. You can see that you can see a small cycle which is formed by the 2,2 and 1,1. Just want to chat a bit more about examples of graphs from real life and from the technology sphere as well. Probably a most popular and simplest example of an undirected graph is a graph of your Facebook friends. If you're friends with someone on Facebook, it means that you have them as friends and they have you as friends. So friendship goes 2 ways. Then another good example is pedestrian pathways. Let's say there is a road where you can walk. You can generally walk 2 ways, right? And that would be an undirected graph. Also, computer networks like LANs, local area networks, are undirected graphs because we say that each node is a computer and each edge is a connection. And if one device is connected to another, then this second device is connected to the first one as well. Again, it goes both ways at the same time. For the directed graphs, you can think of the graph of your Instagram followers. You can follow someone on Instagram, but they might not follow you back. So the search only goes one way, unlike the Facebook friends graph. If you think about roads between towns rather than pedestrian pathways, the roads might not go both ways either. There might be roads where you can only drive in one direction. So that would be a directed link between the two vertices in this graph. And finally, if you think about a big programming project which has multiple files, multiple modules, and some modules might import other modules, then this import relationship forms a directed graph. Because if you import one module from another one, then the second one does not automatically import the first one, and it's for good, because otherwise it would just not work well. Right, so now I just want to chat a bit about graph implementations. And first, let's just look at the left, where we have the this little class for representing a node in the graph. And you might notice that it's very, very similar to the class which we use to represent the tree node, because each node, again, it will have an integer value. It does not have to be an integer in real life, but just for the purpose of this talk and for simplicity, we assume that each node just has one integer associated with it, and that's basically it. And along with the value, each node has links to its neighbors, and they can be directed or undirected. So the somewhat naive implementation for the graph would be to instantiate all of the nodes and then manually link them. And then just pick one node which can reach all of the other ones in the graph and return a reference to it, as it's done here on the left-hand side. It's not very practical. It's a bit far-fetched. This implementation is not very widely used in practice. Another kind of graph implementation that you can use is called adjacency matrix. It's the one on the right side. So in order to build an adjacency matrix, you initialize a matrix of size. You initialize a matrix with n rows and n columns, where n is the number of vertices in your graph. And each element of this matrix is either 0 or 1. And we say that the element of the matrix indexed by ij would be 1 if either I is j, or there is an edge from node I to node j. And you can see an example for an adjacency matrix for this little graph, for this little 4-node graph, which I have in the center. Adjacency matrices are very nice. They're quite easily interpretable. Plus, if we're talking about undirected graphs, these matrices will be symmetric, because if there is a connection from node I to node j, there is definitely a connection from node j to node I. However, there is one drawback of the adjacency matrix, and that is that it takes up quite a lot of space while it can be sparse, which means that if there are quite a lot of nodes in your graph, but not that many edges, you can have a lot of zeros in your matrix, and you will waste your memory, you will waste your disk space on storing this matrix, which is really mostly zeros. So it's not the most practical way to represent the graph. And personally, my favorite way to encode the graph would be to have a structure which is called an adjacency list. Although it's not really a list here, it's more like a dictionary of sets. But the idea is that you list all the nodes which you have on the graph, and for each node, you list a set of nodes which this node has an edge to. So in this case, 1 has directed edges to 2 and 3. 2 has just one edge, which leads to 4, and 3 also has just one edge, which leads to 4. And it gives us this little dictionary at the very center. And you can see that it's very readable compared to the piece of code on the left-hand side. And it's also very laconic and condensed compared to the adjacency matrix. So now I'm hoping to chat a bit about two very key algorithms on graphs, and I'm just going to explain them on a high level. So we're not going to look at the code for these algorithms. We're just going to talk through what we do, to talk through what the steps are. And the problem that I suggest you to think about is, given a graph and given two nodes, which we know are in this graph, can we answer the question whether these two nodes are connected in the graph or not? And by connected, I mean that there is a path from the first node to the second node. So if you start at your first node and follow some of the edges which go out to it, will you eventually arrive at the second node, or will you not? So there are two different ways of how you can approach solving this problem. And these are called breadth first search and depth first search, quite famous algorithms for traversing the graphs. So let's say, let's look at this little graph, which I have here on the right side. Let's say that we want to answer whether node A, which is at the very top, is connected to F, which is at the bottom. I would also like to know that it's funny that this graph is also a tree, but keep in mind that it's not true for an arbitrary graph. All trees are graphs, but it is not always the case the other way around. So let me just check if, okay, yeah, the GIF works. So how does breadth first search work? We start at the node, at the first node, which is given to us, that would be A. Well, the first thing that we do is we check whether it's the node which we want to arrive at. And clearly in this case, it's not. So we have to explore further. Then we look at all the neighbors of this node, and that means all the nodes which A has links to. And in this case, it's just B and C. And we check whether those nodes are the ones that we want. And unfortunately, it's not the case. So we know that we checked all the nodes which are one hop away from A, but we haven't found F yet, so we need to look further. So what we do next is we look at all of the nodes which are 2 hops away from A, and that would be neighbors of B and C, and that would be nodes like D and B, for example. So you take set of all the nodes which are neighbors of B and C. In this case, it would be 4 nodes. And you check whether the node that you're looking for is in this set. Luckily for us, it is, because we're looking for F. But if it weren't in this set, then we would need to check the nodes which are 3 hops away, and so forth, and so on and so forth. So I'm going to play this GIF, which just shows us which nodes we're inspecting at every single step. So we start with A, then we check B and C, then we check all the children of B, all the children of C, and so on.
Yeah, and we have a question here. Is this a directed graph?
So in this particular case, I just assume that the graph is directed, but it does not have to be directed. So it would work with undirected graphs as well. Does it make sense? So yeah, here's just a little write-up. So just to reiterate on this question, you can ask this question about the connectivity between the two nodes, both in the directed graph and the undirected graph. So yeah, it's actually, it doesn't have to be a directed one. Right, yeah. So now moving on, I just want to quickly cover the second approach to this problem. And again, we would assume that it's a directed graph, although it doesn't have to be a directed one. So this is, I apologize, it's a slightly different graph because I was looking for a ready GIF. I was not doing it myself, and I couldn't really find the graph, the DFS, which is drawn in the same style as in the previous slide. So in this case, we'll also start with the top node, which let's assume it's, we'll also start with A, which let's assume is the top node in this graph. But instead of inspecting nodes which are one hop away from A, then 2 hops away from A, and so forth, we would instead aim at inspecting all the paths which start with A. So we will start with this top node, then we will pick one of the children, let's say the leftmost child, and we will try to go as deep as we can into this graph and see if the node which we're looking for lies on this path or not. If it does, great, job done. If it doesn't, then we'll need to backtrack, we'll need to return and try some other path instead. So we're not going level by level in this case, but rather we are trying to look, we're trying to inspect the full path starting at some node. If it doesn't work out for us, we try another path, then we try another path. And I'm going to play this GIF, which is a very nice, illustration of the depth first search. I apologize, the nodes are not indexed with letters here, but rather they're indexed with integers, but I hope that the illustration will still be clear. So you see that we first try the path from 1 to 4, because it's the leftmost path in the graph. Then the next path that we try is 1, 5, 6, 7, which is the second path in the graph. Then 1, 5, 8, and so on. So this algorithm pursues the same goal as the breadth first search. Really, it's just a different approach, and there are pros and cons to all the approaches. Right, okay, again, stop there. I think we are overrunning slightly, so I'm really keen to move on to the problems. However, if you have any final questions before we go into the problems, feel free to ask.
Okay, there is a question. What are the pros and cons of this approach?
Okay, so in the for example, let's think that we want to find, instead of just checking if the two nodes are connected or not, we want to find the shortest path from one node to another node. And in a general graph, there can be multiple paths from one node to the other. If you choose the depth first search approach, there is no guarantee that you will find the shortest path first. So you might find out that the nodes are connected. However, there might be some other path down the road which is better, and you'll need to try all of the paths from nodes A to B in order to find out which one is the best one. When you go breadth first search, it is guaranteed that you inspect all the paths of length 1, then length 2, then length 3. So you'll find this, the shortest path straight away. For example, in the breadth first search, the downside of the breadth first search, on the other hand, is that the graph can be very big and very densely connected, and you need to keep track of all the candidates that you're going to check on each of the level, and that can be quite a lot of nodes. So you'll have to store them somewhere. But I would just like to note that the two algorithms have the same complexity. They all run in linear time with respect to the number of vertices and edges. So they are equally efficient. So really it's a question of what task are you trying to solve. I personally prefer breadth first search, I think, and I just like to note one big advantage of this algorithm. So let's say that you've got a graph and you want to print the graph, and you have some dependencies within the nodes clearly, and you want to print the graph so that first you print the nodes which have no dependencies, then you have the node, then you want to print the nodes which are only dependent on the nodes that have already been printed before, and so on and so forth. So why is it an important task? Imagine that we are talking about some computational pipeline which consists of different tasks which have dependencies between each other, and you would like to execute this pipeline so that all the dependencies are satisfied. So you want to pick the nodes with no dependencies first. Then whenever you move on to the next tasks, you want to make sure that the dependencies have already been satisfied. So this kind of printing of the graph is called topological sort, and you can do it with both BFS and DFS. However, if you do it with BFS, you have a nice benefit of being able to parallelize your execution, because first you might find a node which have no dependencies at all. You can launch them in parallel. Then you're finding the nodes which are one hop away from the roots that you just executed, and you can launch them in parallel. And then you can launch the nodes which are 2 hops away from the roots, and so on and so forth. And if you run topological sort with BFS, it just gives you these groups, these levels in the result right away. I hope this answers the question. So let's move on to the practice tasks now. So the first one is called N-ary tree Preorder traversal, and I have the link to the LeetCode problem here, so you might want to open it. So basically, let's say that we have a tree where each node has an arbitrary number of children. So it's not binary, it's not a quad tree. Each node can have as many children as it likes. And what we want to achieve here, we want to print the tree in the following manner. We want to print the value of the node itself first. Then we want to print the values in all the subtrees of its children. So if you remember, we covered a similar traversal today for binary trees. but it will first print everything to the left-hand side, then the node itself, and everything to the right-hand side. So I encourage you to look at that little program and think how you can modify it for the trees with an arbitrary number of children in each node, and also with printing the value of the node first.
Yeah, sounds good. So we are ready for breakout rooms, yeah?
Yeah. So this is just a quick reminder of that first algorithm, which you might want to take a note of. But yeah, happy to go to breakout rooms now.
Yeah, and I'm stop recording for now. Thank you very much for this presentation.